If we think of permutations as counting the number of ordered lists, then combinations are counting unordered sets. Let's suppose that the order of pizza toppings doesn't affect the pizza. And let's imagine that there are 5 toppings: pepperoni, onions, hamburg, banana peppers, and spinach. And let's ask our question, how many 2-topping pizzas are there? Well, if order did matter, we would have a pepperoni and onion pizza, or an onion and pepperoni pizza, a pepperoni and hamburg pizza, or a hamburg and pepperoni and banana peppers, or banana peppers and pepperoni and spinach, or spinach and pepperoni, onions and hamburger, and hamburgers and onions and banana peppers, or banana peppers and onions and spinach, or spinach and onions, hamburg and banana pepper, or banana pepper and hamburg and spinach, or spinach and hamburg, or banana peppers and spinach, or banana peppers. Since we said that the order doesn't matter, our number of actually distinct pizzas is less than this. By counting, we can see that the number of ways to permute these 5 toppings into just 2 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The number of combinations of 5 objects choosing 2 is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we see 2 things. 1, that the number of combinations is fewer than the number of permutations, using the same n and k. And that 2, here, the number of choices of 5, 2, so 5 choose 2 equal to 5 permute 2 divided by 2. In general, if there are n objects to choose from, the number of k-sized unordered sets, n choose k, is equal to n permute k divided by k factorial. The only reason we didn't see a k factorial before was because 2 factorial is just equal to 2. Because this formula includes another formula, there is, of course, multiple equivalent ways for us to find n choose k. We could say it's n times n minus 1 times n minus 2 and keep counting down until there are k terms being multiplied, divided by k factorial. Or we could choose our most concise representation of n factorial over n minus k factorial times k factorial, where this first part, n factorial divided by n minus k factorial, is exactly that n permute k. So to do an example, let's say there are 15 students. How many ways are there to choose 4 students to make a group? Note that forming a group is different than lining them up, because lining up the students has an inherent order. It's an ordered list of students. But forming a group, there isn't someone that's in first, then second, then third, then fourth. It's just a question of which student is in the group or not in the group, meaning this is more akin to an unordered set of students. So this question is asking us to find 15 choose 4. Again, there are multiple ways that we can go about counting this. We could start at 15 and keep multiplying by terms that are 1 less until we have 4 terms. So 15 times 14 times 13 times 12 divided by 4 factorial. So 4 times 3 times 2 times 1. Or we could use our formula, which is 15 factorial over 15 minus 4 factorial times 4 factorial. 15 minus 4 is 11, so this is the same as 15 factorial over 11 factorial times 4 factorial. And because 15 factorial is 15 times 14 times 13 times 12 times 11 times 10 and on. And 11 factorial is 11 times 10 and on, times 4 times 3 times 2 times 1. We'll see that we end up with the same two answers of 15 times 14 times 13 times 12, all divided by 4 times 3 times 2 times 1. To find a final numeric answer, we can cancel out some terms common to the numerator and the denominator. Here, 4 times 3 is 12, and 14 divided by 2 is 7. So 15 choose 4 is also equal to 15 times 7 times 13, which is equal to 1,365. So there are 1,365 ways to form a 4-person group out of 15 people.